Hello, everybody. We are going to now start the discussion on the general mass balance equation, which is going to be the equation that we will use to describe any unit or any process or express the balance of mass in any process. And we are going to go through some examples in order to understand the terms that we have in the equation. So the main concept in this, that we are basing our equation on, is the concept of conservation of mass, which means states that the mass is neither created nor destroyed. And from this we can start. The first example that we will check is the example of a mixing unit where we have 10 kilograms of water mixed with 5 kilograms of ethanol, and we don't know what is going to be the product. Now, this is just a simple mixing unit. We put the two components together and get them outside on the other side as a product. So if we apply the mass balance or the rule of conservation of mass on this unit, we can easily say that the amount of water that is in is going to be equal to the amount of water that is coming out. So we have 10 kilograms here, then we will have 10 kilograms here. The same for ethanol, 5 kilograms here and 5 kilograms here. So from this we can start with the very simple logical terms that we can have in the equation, which are the term of in equals out. So this is the first thing that we can learn from this example. In the second example, we have a combustion unit, and in this combustion unit, we have air going in. Air consists of oxygen, nitrogen, carbon dioxide, and we have fuel that is fed into the combustion unit where it burns with air to produce heat, and then we have a gas coming out. So, based on our basic and simple understanding of the combustion, it's a reaction between a fuel and oxygen. So we if we apply or we try to apply the same concept that we used in the previous example, on this example we would think that the mass of oxygen out is equal to the mass of oxygen in. But this is not logical, and the same for the carbon dioxide. We have only 1 kilogram per hour carbon dioxide in, and we cannot say that it's the same amount that's going out. And this is because the oxygen is being consumed in the combustion unit. So the 23 kilograms per hour will come out as maybe 3, 4, 5, whatever, but it must be less than the carbon dioxide, the oxygen that's going in. The same for carbon dioxide. The carbon dioxide is a product that comes out due to the combustion. So the combustion of carbon dioxide makes the amount out that we have here is more than the amount that we have in the feed. So in this case, we cannot say that mass in is equal to mass out, because there is some of oxygen that's consumed and there is carbon dioxide that's produced. So we have to account for this when we write the balance equation. So the oxygen consumption and carbon dioxide generations are something that we have to include in our equation by adding a term for generation and a term for consumption. So this is, we haven't gone through how these terms will look like, but I'm just talking about the terms in general. This is why we need to have a term that represents the generation, and there is a term that must be there to represent the consumption. For the last example that we have here, we have a very simple example where we have a tank that is being filled with water, and this tank or bucket has a hole at the bottom, and this hole is draining water. And the rate of flow of water into the tank is more than the rate of the flow of water outside the tank. This is just a simple tank. There is no reaction, there is no consumption, there is no generation. So we have, in this case, mass in and mass out. But can we say that the mass in is equal to the mass out? Of course not, because we know that the flow rate of water going in is more than the flow rate of water going out. So in this case, the difference between the mass in and mass out is the accumulation, that the increase in the amount of water with time. This is what we describe as the accumulation. So in this case, the difference between the rate in and mass and rate out is the accumulation. So now we agreed that we have 5 terms in the equation, and these 5 terms are mass in, mass out, generation, consumption, and accumulation. And based on this, we can write the final form of the general mass balance equation. So we apply this mass balance equation on any system, but before we have to agree on this term, which is the control volume. So the conservation of mass equation on a control volume means that you have to decide what is the unit, or what is the system that you are applying your equation on. So for example, if I apply my equation or the balance equation on unit 1, so I'll be only concerned with this stream, and this stream. If I apply it on unit 2, then I'll take into account these 2 streams and these 2 streams. Okay, this is an intermediate stream, so I'm not going to account for it. I'll consider these 2 as a black box. The same thing if I apply it on the 3 units, then I will only care for the streams that cross the boundary, this green dotted line. So it's important before we apply the equation is to decide what is or what are the boundaries of our system before we apply the equation. The equation is going to be the summation of the inputs, and we put the sum of the inputs because, like in this case, we can have more than one input, plus the generation, which is due to the reaction, minus the summation of outputs, which are the red streams here, minus the summation of consumptions due to the reaction, one or more, is equal to the accumulation of the material. This can be applied to total mass, meaning that I can apply this equation on the total mass of all the components that are there in the system. It can be applied on the mass or mass flow rate of one or multiple species if I have more than one component. The same for the moles for one component or more. There is something, it's not very accurate here, but I'll fix this later, that the application of the flow rate, the total flow rate, is valid for all cases. The applications of flow rate of one or multiple species, I think it's correct here, that it's fine. The application for all cases, the application of the total molar flow rate is valid if there is no chemical reaction. Okay, so if there is a chemical reaction, we cannot apply the total number of moles because the reaction can change the number of moles. So the total number of moles here is not right, and the same for no, but the molar the number of moles of one component is fine. We'll go through this later, but I just wanted to give a hint here so that it's clear that we need to be careful if there's a reaction when we deal with the total number of moles. It can be applied on a single unit or a collection of units as we agreed. There is one important thing, we mentioned this before, but I want to stress on this because this is important, that the units of all the terms in the equation must be homogeneous, meaning that we have all these 5 terms, that if I use kilogram per hour for one term, that all of them must be kilogram per hour. If I use pound per second, they all have the same unit. If it's gram mole, then all of them must have the same unit, and so on. So this is something that you need to be sure that you do correctly before you substitute or you get the final answer. Okay, so now the equation has 5 terms, which might be hard to deal with, especially with the accumulation term. It is a differential term. So when we deal with these kind of equations, there are cases that we deal with a lot. And these are going to be the cases that we are going to cover in this course, inshallah. So these cases are the case of steady state, when there is no change on time with time, so there is no accumulation. So this term will be cancelled, and then we have only input plus generation minus output minus consumption equals 0. And this is the equation that we use for reactive systems. And if there is another case if we have steady state and there is no reaction. So this is what we call the non-reactive system or the physical system. So there is no accumulation because it's steady state. There is no consumption, no generation because it is there is no reaction. So the final form would be input equals output, or summation of input minus output equal 0. So this is going to be used in, as I said, the physical systems or non-reactive systems under steady state conditions. So this is all what I want to discuss regarding the equation. So we know the equation. In the coming videos, we are going to go through some examples, and these examples are very important because we need to understand how we can express these streams of input and output. How can we express the generation and consumption? These are all things that we need to go through in details starting the next video, inshallah. So I'll see you then.